Hello folks, this is Todd Coburn of Cal Poly Pomona with Lecture 8 of Aero 3271. Today we're going to be continuing our discussion of fracture mechanics and extending what we learned last time. Let's take a look at how that works. So remember we started by looking at fatigue, and we saw that in fatigue we're just characterizing the stress life properties of a perfect sample and then converting it to something that's closer to what our sample is. With damage tolerance, we took this different approach. We looked at the mode 1, mode 2, and mode 3 cracks. And we developed our approach last time where we came up with the stress intensity and compared it to the critical stress intensity. And to do that, we had to be able to find the right mod factor. We then learned how to determine whether a structural part with a given or assumed crack is expected to experience fast fracture under the stress level and crack size that we find. And we learned how to predict how big the crack would be at fast fracture. Okay, so today we're going to look further and take a look at some other ideas that extend this. To start with that, take a look at this chart up here on the upper right. And we see what we've done is, following some testing, we've got a plot that shows the number of cycles on the horizontal axis versus the crack length on the vertical axis. And if we plot that out as we increase the number of cycles and the stress level on the how that crack changes as a function of that, we find curves similar to this. If we take a part and the delta stress level, or the max minus the minimum stress, is of a certain magnitude, we get a figure like the first curve shown. And if we put more change in stress, maybe we increase the max or we decrease the minimum, we get a curve like the second one. And if there's an even larger change, we get a curve like the first. Now these aren't linear, so they're kind of difficult to predict unless we can curve fit in them in some way. But we see, okay, starting off we have part of the curve that looks like it's rather benign. It grows but rather slowly. And we have a part of the curve that grows rather abruptly, corresponding with fast fracture. And between there we have a part of the curve that if we just pretend that that's a straight line, we could look at how that crack changes, how the crack length changes as a function of the number of cycles. Now we're going to use this idea. We see then, though, the major thing we see here is that if we have the larger the change in stress that's applied to the part, the more drastic this becomes. Okay? So we see that the life of the part as it's cycled is a function of the change in stress. We saw a similar thing with fatigue, because in fatigue we saw that it was both the mean component, which is a measure of how high the stresses get, and the alternating component, which is a measure of how much they change. In the same way, we see that same change in stress from max to min being a factor in determining whether we have a longer life or a shorter life. Now if we characterize our stress, now before we introduced the stress intensity K1 as beta sigma max stress times the square root of pi a. And because we're seeing here that this change in stress is actually something that affects the stress levels, we can take that same stress intensity curve, and instead of looking at the stress intensity itself, we use that for fast fracture. We can look at the change in stress intensity from the maximum to the minimum stress. So the change in stress is just the max minus the minimum stress. And look at that change in stress intensity factor. We then can plot. And if we plot this on a regular curve, it doesn't show a great trend. But if we plot it on log curve, so we take the change in length of the crack divided by the number of cycles, and plot that against the change in stress intensity. If we make that plot on this log-log curve, we're going to find a relationship like this. We've got a part where things are increasing abruptly, and then it has kind of a linear relationship, and then it changes abruptly again. And that abrupt later change is associated with fast fracture, and this linear portion of the curve is where most of the crack growth occurs. And if we could just figure out what this equation of the curve is, we could use this to approximate or estimate how long a part will last. One other thing we can note that we're not going to do anything with is that we actually get a family of curves, and if we have a larger stress ratio, where the stress ratio is defined as the minimum to the maximum stress, kind of like we saw in fatigue, we see that that also affects those curves, okay? So based on that, this is kind of the background information that we're going to use to develop our approach. Okay, we can actually curve fit this linear portion of the curve with this equation dA, the change in crack length with respect to the number of cycles in that increment of time, will be some constant times our change in stress intensity to some power. We're going to use the same table as we did to get our critical stress intensity for the material. Remember, our critical stress intensity was determined from this table here, and we're also going to get our two constants from that same table. So basically, these constants, C and M, are a function of the material, just like our K1C was, and we can get it from the same table. So we're going to go and get those, and we're going to use this equation to approximate how that crack changes. We already know how to evaluate fast fracture as a function of our crack length, and we can use this to say, well, if we have 1,000 cycles, we can use this equation to find out how much that crack length should change. 10,000 cycles, we use this equation to find out how much it changes. Now, you'll notice that this constant C is not changing and the power M is not changing, but the change in stress intensity is a function of both the max minus the min stress, which is not changing as this process goes on, but it's a function of the A, which is changing, and of the beta, which are changing. That's going to be what makes this difficult to calculate. Now, if we want to do a nice accurate number, we could use continuous or numerical calculus to actually evaluate this equation. Okay, that's what we're going to see on the next slide. So here's our basic method for fracture mechanics. We're going to start by using this equation. We're going to find what our max and min stresses are. We're going to plug that into this equation with the beta that is associated with this and the pi a. So that means we're going to take our start. If we take that equation and recall that this is the equation dA dN is equal to C delta K to the M power, we could integrate this puppy as shown here. If we integrate as shown there, then we can find that the number of cycles by just solving that, which gives us this equation, which means if we have M and our change in stress on our beta, and because beta is actually a function of this change, so normally we can't remove beta from the integral, right? Because beta is changing as the crack length is changing. Both the A is changing and the beta is changing. But that makes the calculus difficult for most people, and therefore what we're going to do is pretend that beta is in the equation above here, that we're going to pretend that that beta doesn't change. And in order to do that, we're going to just plug in the average beta. Now this is going to introduce some error into our calculation, so this method is approximate. Even though this is approximate method, there are various numerical things we can do to correct this error, and actually we need quite a number of cycles of iterations in order to match the accuracy of this simplified approach. So what we're going to do when we use calculus, continuous calculus, to estimate the number of cycles is we will figure out what our beta is initially, what our beta is finally, and we will take the average of those. We'll then plug that average into this equation, and now we can integrate it, the solution of which is shown here. And then we can use that to estimate the number of cycles to failure from the time we find that initial crack until failure. If at any time in the life of the aircraft we go and inspect that part to verify what the crack length is at that point. We can actually certify the aircraft for more cycles if we use that new crack length and apply this equation again for however many cycles we need to have left. Okay. So here's a couple little notes. This is reminding us how to integrate. This is actually rather simple, while this kind of integral where we have an a on the bottom, the square root of a, is rather tricky. The way I've shown it here is pretty straightforward, and this is just our approach. As long as our m value is not -1, if it's -1, then we have the natural log of that, whatever the integrand is. But in most cases, we're going to end up finding that our coefficient is -m/2, which is generally not -1, and therefore we're going to use this upper one to integrate that puppy. Now the other way we can do this, so that's how we're going to solve this with calculus. If we want to solve this numerically, we can do the same thing by just rearranging this dAdn equation. So we calculate the change in crack length as a function of number of cycles. We then choose a number of cycles, like some increment. Let's say we want to evaluate the change. We could say, okay, I'm going to go 10,000 cycles, apply this equation. I'm going to use beta from the initial. You go 10,000 cycles, I calculate the change in crack length, and so on. And using that approach, we can evaluate a numerical estimate of the final crack size. What you're going to do is either use calculus or you'll use a numerical approach, and I will tell you which one to use. So let's go ahead and clarify our method then. If we're going to use calculus, what we're going to do is we're going to determine our K1C from the material from our table in the handbook. We're going to go and figure out from the problem statement what's our initial crack size, and we're going to use that when we determine, also look at our loading to calculate the beta initial for the part. We're going to figure out our maximum and our minimum stress, far field stress applied to the part, and we're going to use all of this information to calculate our, first we're going to calculate our stress intensity. In a moment we'll also check our change in stress intensity, okay? So once again, we plug in here to get the stress intensity, and we evaluate whether we're already at fast fracture or not by comparing that stress intensity to our critical stress intensity, okay? Then what we're going to do is we're going to take that value, we're going to figure out what our final crack size is. Now, if we're going to use calculus, what we're going to do is take our first estimate of beta 1, like we talked about last time. We're going to use that to calculate our final crack length, and we'll use that final crack length to determine our beta final. We'll then take the average of those as shown here, and that's what we're going to use in our calculus equation. Every time we use calculus, we use this approach to determine beta average. Once we have that, we're ready to find our coefficients of the material, which we can get from the same table as we got our K1C. And then we plug into this equation, we solve this equation, which is actually taking a continuous calculus solution. This will give us rather accurate results for the problems or for the approximation that we made. Now, this procedure is a little more clear than what I put in the handbook. So it augments it, but is clearer. So what you want to do is print this slide out, shrink it down, and stick it in your handbook on one of your pages that have room, at the bottom of page 4.4 or 4.5, or on one of the extra pages. There are a few pages, 4.12 and 13 are also blank pages for you. Okay. Now, that was how we do it using calculus. If we want to solve it numerically, we're going to use a similar approach, and here's what it is. We're going to once again figure our K1C and our initial crack size. We're going to get our max and our min stress. We're going to calculate beta for that initial crack size. All this looks the same as before. We're going to get our change in stress intensity by plugging in the max, the min stress, and the beta and the A. We're then going to, using this equation, we're going to rearrange it like this, and we're going to plug in our coefficients, our C and our M, with these other pieces of information. We're going to assume some increment of the number of cycles. So what you want to do is look at how long does it look, does stresses look high or low? Do you now if I say use a certain number of increments, what you can do is say, well, if I'm saying, if I think it's going to go a long time, I choose like 1,000 cycles or 10,000 cycles or whatever. You plug in that little delta N, you calculate how much the crack size changes. Okay? That's how much it changes. You then, as shown here, here's your equation. You're going to use this equation here to calculate the change in crack size. Now, once you have the change in crack size, you then can calculate a new beta for that new crack size. Remember, the new crack size, actually, it's not clear here. You take the change in crack size, you add it to your original crack size, right? That's the new crack size. Then you take that crack size and calculate your beta for it. And you calculate your K1 for it. And you can evaluate fast fracture. Are you yet at fast fracture? If you are, then you've just passed the allowable to part. If you aren't yet, then you can continue this approach until you find what the total cycles are to failure. When you're all done and you've converged on the problem, you can calculate your total cycles by just adding all your numbers of cycles, okay? Got that? So this is also a little more clear than what's in your handbook. It's just kind of in a little bite-sized piece. You're going to want to plug this into your handbook as well, okay? Now, another method, if we want to say, okay, well, let's say we want the crack length after n cycles, we could actually use that last approach or use a slight modification to it, and that's what's shown here. We're going to get our K1C, our max stress, our initial crack size, our beta, and then our stress intensity for that beta. We evaluate fast fracture, and then we break our cycle, choose an increment of delta n. Here's some examples of what you might use. Then we're going to go and estimate the change in crack size using that same equation, add our delta A to each one, and keep going until we find the number of cycles to failure. We then can add those together. So if we look at a basic example, let's say we have a part like this. This looks quite similar to our handbook. Looks like we can go and grab the stress intensity from that spot. Let's say we have these stresses on the thing. The max stress is, now it doesn't matter if we have a stress, let's say we have 60 KSI is one stress that we have on it, 50 KSI, we have a 30 KSI, we have a 0 KSI, we have a minus 20 KSI and a minus 5 KSI. We're going to take all those, take the maximum value, 60 KSI, and the minimum value, minus 20. Those are our max and min. Okay. Let's say we want the number of cycles before catastrophic crack growth. Well, here's our approach. We're going to go and use this figure to calculate our beta, like this, right? That's our initial beta, and now we're going to need to get our final beta. Actually, the two methods that I gave you are slightly different. Here, if we're going to use calculus, we would do this, calculate our final crack length, and then our beta final based on this approach. Now, if we're using calculus, we would use this to approximate our beta average and then go through calculus. If we're doing a numerical procedure, we could go ahead and just continue to iterate, assuming larger and larger crack sizes. Now, this approach is slightly different than what I just presented. I used to have students do this way. I've found that I think it's more straightforward to use the process that I just gave you on the last couple slides, which basically means if we're going to use calculus, we will take the initial crack size and calculate an initial beta, and then we will use that initial beta to calculate a final crack size, and then we'll calculate the final beta for that final crack size, and then use the average beta of those two values, which is like our first two steps here. To calculate the final crack length at fast fracture, rather than this approach, which is a numerical approach to get there, we can just go through the process that we were talking about before until our answer converges on the final crack size. The place where this procedure works a little better is if we're not certain. This takes out the uncertainty of what delta n we're plugging in and allows us to creep up on the final crack size to get a better estimate of the beta average. Okay. Continuing now, once we have our beta average, We then can come in here, if we're going to find how many cycles we're good for by calculus, we're going to go ahead and find our C and our M, plug into this equation, which looks like this. This is kind of wacky looking because I've done it in Excel, but this is the way it lays out. Put in your values and then calculate how many cycles you're good for. You'll notice we're using the beta average that we found on the last slide. We've got our initial and our final crack size, and that gives us an estimate for the number of cycles. Now, if we had to be good, let's say this part needs to survive for 10,000 cycles, then obviously we can see that our margin of safety is negative because it would be 136 over 10,000 minus 1. If we only need to be good for 30 cycles, we're going to have a positive margin of safety because we're going to have 136 over 31 minus 1. That's our answer. And that gives us, actually this approach is about a 6% error because of that approximation we used with beta average. If we had done a better job of integrating this numerically, where we're accounting for both the crack size and the beta, we would have got a little better answer. But actually this is one of the approaches that we're going to use to estimate the life of the part. Now, if we use a numerical solution of the same thing, we could use this equation with various estimates. Let's say we try to solve this in a single step. So we would use this equation for delta A, and we would just keep plugging in. We take our beta initial and our change in stress with our coefficients and our initial crack size, and we just keep on changing our N until we get a negative margin of safety, or a zero margin of safety, and that would be our estimate. Now that would have a huge amount of error associated with it, and just one evaluation of 10,000 cycles jumped over our K1C. What this is doing is we would be applying this until our K1 is equal to K1C. So if we're using a single approximation, we would have to iterate like this. Let's say we're trying to get there in one step. We iterate, we guess 10,000 cycles, and we find we exceeded K1C. So then we guess 1,000 cycles, and then we find that we're still exceeding K1C. So we guess 500 cycles, and we find that we've got a small margin of safety. Now we could stop here or make one more guess, say 550 cycles, and we're pretty close, say 540 cycles, and we nail it almost one more time, and we basically get roughly a zero margin of safety. So you'll notice we just iterated 1, 2, 3, 4, 5, 6 times to find the answer. But each of these is based on a single step going from the initial crack size to the final crack size. That introduces all the error associated with our beta 1. We're using beta 1 in all these cases. We didn't change it, so that introduces a lot of error. This is completely wrong, even though the approach is a valid approach. In fact, if we look at what this is compared to the actual answer, it's about 5 times too large. We're not good for 545 cycles. We're good for something much less. Remember, calculus said we're good for 136 cycles. This single step numeric approach is completely wrong. Completely wrong. Why? Because of the assumption. Remember, the calculus approach uses beta average, a rough approximation of beta average, and I told you before it's about 36% off. That sounds like a lot, but 5 times the solution is a lot more. Got it? Now, if we're going to use a numerical approach using this equation, what we need is more steps. Let's take a look at how, if we had used more steps per iteration, how that would have come out. For example, let's try iterating in 7 steps. So let's just make a wild guess and assume 70. Let's say our next approach is to try and do this numerically, and let's say we start with 70 cycles. If we guess that we have a change in stress level of 70 cycles, we start with our initial crack size, we calculate our beta, we calculate our delta K1C, we say, okay, we're going to apply this for 70 cycles. We plug into this equation above, and we calculate the change in crack size as shown here in the 5th column. We then calculate the new crack size, which is just our initial crack size plus that change in crack size. You see that? Column 6. Then we calculate our K1 for that new crack size. Okay? If that has positive margin of safety, we continue. We now take that AI plus 1, 0.1204, and go to the next step and use 0.1204 in step 2. We calculate beta, we calculate our delta K. We plug in the 70 cycles, and then we calculate our delta A. We add that delta A to our initial, which was 0.1204, to get a new final crack length. We calculate our K1, and we find we still have positive margins. So we take the crack length of that step and bring it to the next step. Calculate beta, calculate delta K, plug in our N, calculate the change in crack length. We add that to our initial crack length to get the final crack length. Calculate our K1. Still barely positive margin. We take the crack length from there, start again, calculate beta, calculate change in crack size, plug in our numbers of cycles, and we pass the solution. We exceeded K1C. Now we could have actually just changed this last step. Instead of increasing by 70 cycles, we could have increased by like 10 cycles or something to try and nail it and just iterate that last step. This would be a 4-step solution, and this also has error associated with it. If instead we had chosen, this is another attempt to approximate this, if we had chosen 35 cycles and go through the same approach, then we find out we get 6 cycles before we converge on the solution. If we instead assume 25 cycles, we now have in 7 cycles we found the answer, and now we're saying if we add up all these n's together, we have a estimate about 173 cycles. This numerical approach thinks that we're good for 173 cycles. Okay? Now, if we were to do this in more detail, this is also a little too large, about 30% too large. If we had gone through a 40-step iteration, we would play with this until, if we just increment by 3 cycles, so we calculate, let's look at how this works. We have our initial crack size shown in our first row. We calculate beta, calculate delta K. We say, okay, let's just let it, now the best we can do is like 1 cycle. Every cycle we calculate a number, right? But let's go a little quicker. Let's assume 3 cycles. If we go 3 cycles of that, we calculate our change in crack length. We add that to our initial crack length and get a new crack length, calculate our K1, and we get a positive margin against K1C. So we take the final crack length, bring it to the next step, that becomes our initial, and go through the process again and again and again. You'll notice each of these times we're plugging in 3 cycles or whatever our assumed number of cycles are. When we're all done, we would find slight positive margin after 40 steps. And if we add all of our little n's together, we get 100 steps. So this 40 cycle solution actually is pretty close to what actually happens. Now, the only thing better we could do is if we did this process and followed every step. So every time we only have 1 cycle, we take our beta 1, calculate the change in crack length, and we get a final crack length, and then get a new beta for each and every step. That would be the best we would do, and that would be like an exact kind of number. Of course, that's a huge amount of work, and at least with simple tools, and so these other approaches give us an estimate. We could actually assume that this 100 cycles is roughly the solution. That's why our calculus solution was 136 was wrong, but not too bad, about 36% off. You'll notice that of all the numerical approaches, we needed about 7 steps before we got close to that same level of accuracy. If we try to do numerically in 1 step or 5 steps, it's going to be worse. If we do like 10-ish steps, we're going to maybe be a little bit better. 40 steps, that would be good. That'd be hard to do on like a test. So what we're going to do is use calculus, and we're going to use numerical approach. Now, If I do give you the numerical approach, while I looked at a number of little things here to study out how this played out, let's say I tell you on a test I want you to use a numerical approach. That means we're going to use this equation right here, right? And let's say I want you to use 10 steps. So what that means is you're going to take your first iteration where you put in your first initial crack length and your beta initial and your delta K1 initial, and then you're going to grab some number. Let's just assume 50 steps. We calculate our delta A and we add that to our initial, add these two together to get our final crack length, or our, this is the crack length at A plus 1, right? We then calculate our K1 at A plus 1, right? Actually, it's not exactly at A plus 1, but for that crack length and that same beta, we can calculate our K and compare it to K1C to get our margin of safety. Make sure as long as this, and actually you don't need to calculate the margin, as long as this value is less than K1C, you continue. Then you take this value, plug it down here. Now let's say this margin of safety is huge. Well, then you're going to want to increase this a lot more, like say maybe 300 or something cycles. If this margin was really small, you might go down to like a 2 or a 3. If you're completely off, you might start over in the table, okay? So basically you're going to say, okay, let's guess, say 50, and then we guess, oh, based on a result, maybe 300, and then maybe 200, and then maybe 300 or whatever, until we converge our solution. If I tell you iterate at least 3 times, then you're going to want to do at least 3 steps. Let's say you do 2 steps, or let's say I say give me a 5-step solution. You're going to do this 1, 2, 3, 4, and now based on what you have, you're going to try and guess whatever this, or iterate this last guy until your margin of safety is roughly 0. And then you, when you're all done, you're going to add the number of cycles and sum them up, and that becomes your number of cycles to failure. That's how we're going to do this numerically. So last time you learned how to evaluate fast fracture and the crack length at fast fracture. This time we learned how to go and evaluate the total number of cycles to failure using either calculus or using numerical approaches. If we use calculus, we're going to use a simplified way of getting our beta final, and we can get pretty good answers without a whole lot of hassle. If we're doing this numerically, we're going to need to work a little bit, think a little more as we go through the process to try and get a good, accurate estimate of what our final number of cracks are, what our final number of cycles are. If you write in MATLAB or Visual Basic or any other of those programs, Python or something, then you can actually develop a little program that will nail this every time by just using that equation and just recalculating beta at every single step. If you do that, you should get really good results. Got it? Enjoy.